your idea? That's just a link. It's like a little clear where title is and start. That's like doesn't really matter for me. It only matters if it's changed to the person. If you send this to me, I can like write up some more stuff.
Yeah, sure. I want to send it to your number or email?
Probably email.
Your email or like your personal?
Yeah, email.
What's your email?
I'm gonna show them.
All right, everyone, so we'll get started with the 7th lecture. If we have a couple of people coming in late, they can join us. In the meantime, if you guys haven't signed in, make sure to do that, as that helps with future ML lectures and other club programs and activities that we do. In this lecture, we're going to be covering PyTorch, which is a popular industry framework for machine learning and a lot of AI tasks and computations. My name is Kartik, one of the ML lecturers. This is Alvin, he's the education lead. Alvin, if you want to wave to everyone. He's our head of all the ML lectures. And then, so like I said, PyTorch is kind of like our main ML and AI framework that we're going to be going over. And so first of all, what exactly is PyTorch? What's its use cases? And why do people use it a lot? Well, first of all, again, it's an industry-leading framework built for performance and flexibility with a lot of AI software. The main component or the main benefit of this is the tensor-based GPU support, which I'm sure a lot of you guys might have used NumPy or similar libraries. The differentiating factor between PyTorch and NumPy and these other libraries is that it allows you to compute and have these algorithms run on the GPU, and therefore you can run more expensive and computational tasks, as well as there's other APIs that you can use with PyTorch, and you can leverage some other functionalities. Again, PyTorch, like a lot of these other Python libraries, is Pythonic in the sense that it has kind of this intuitive coding structure, and it's pretty easy to write, right? So if you like call a variable, or if your last line is just a variable name, it's going to have things like magic printing and stuff like that. You won't see that with other languages, which is why this framework also works in such a way. And then, okay, we also have this huge community and ecosystem that supports PyTorch. We have a lot of developer feedback, a strong developer base that supports PyTorch. A couple of core applications and use cases for PyTorch. I'm not going to get into too much detail, but its main supporting or core applications are computer vision, NLP, and research. So pretty big areas in ML, pretty useful things. If you guys want to kind of get into those areas, then PyTorch is definitely one of the main frameworks to go. I mean, the other competing one that we covered in the last 2 lectures was TensorFlow. That's also a pretty good framework. A lot of people prefer PyTorch because sometimes it has a little bit of intuitiveness with some of the things that it does, and it manages something, it has a higher level abstraction that you don't have to like go too much into the nitty-gritty with things. Okay, so one of the first things that I mentioned was a tensor. So what exactly is a tensor, right? A tensor, you could think of it as a core data structure for basically like any sort of ML or any sort of specific to this PyTorch. And it's similar to any like multi-dimensional array, but again, it has enhanced capabilities and enhanced supporting factors to it that help us do things like gradient tracking, optimizations, and it's basically engineered to have high performance because again, you can do these fast and vectorized operations with GPU acceleration. So in this code snippet we see here, we have we basically initialize it like basically a NumPy array where we have, okay, 1.0, 2.0, 3.0, and then you wrap it around torch.tensor, and there you go, you have your tensor. So nothing too complicated, and we'll see during the demo why it's pretty useful. And you can kind of see it already here with these kind of like these operations that you wouldn't really be able to do any sort of traditional Python array. And then eventually all of this type of stuff builds on. You can also see you can kind of put it on the device, which would be your GPU in this case, and then you have this hardware acceleration component to the tensor. So going kind of a little bit more deep into gradients and optimization, tensors and basically the PyTorch library support automatic differentiation, where if you kind of have something set, then you can basically do a backwards step and kind of see the gradient for that. And then when you have different machine learning concepts like gradient optimization, gradient descent, these types of things can be very useful. And then you can also set up your loss function, which is basically measuring the errors of your designated task, right? So if we have like a linear regression task, our loss function would usually be something like mean squared error, right? We're trying to measure how far off our predictions are from our actual model, right? So that's our loss function. And then our optimizer is basically what's updating the internals of our model, right? So in this case, we have neural networks. We're updating the internals of the weights in this case. And then PyTorch also supports definitions for base class for models, right? You see here, basic object-oriented programming with class model. You can define the initializer, and then basically that's going to be your layer section where you can define certain layers. You can define your activation functions, kind of what we went over last semester. So that's basically your neural network architecture kind of in a linear way. And then you have your forward pass layer, which is basically what happens at inference time when you run through all the layers to get your final output for whatever task you have, right? And then we have our training loop, which a training loop is not necessarily PyTorch specific, but you can leverage, again, the optimizers, the losses, and you can call in your predictions all through, and then kind of leverage PyTorch in that sense. Another thing that I find quite useful for myself is kind of building data sets using the Torch utilities. And so you can kind of have like a custom standardized access to the data, right? And then there's like kind of like a Pythonic interface to this as well. So you can just basically, like we defined the model with class model and then dot module, and we kind of have that subclass. You can do the same thing for your own data set, right? And you can say, okay, initialize that. We have, I guess, what would be our data, right? And then you set any internal variables or properties that you want to set. You have some length, you have a getter function for your length of the data set, and then you can access each individual item, which would be important during training because, again, that's what you're doing. You're pulling in data, calculating the loss, running your optimizer, right? So you want that get item function, and usually in this case, right, you'd have some sort of logic depending on your problem, but in this case, we're basically setting x as whatever we imported here, and then x times 2 would be our y label. So x would be our kind of like our training value, and y would be our truth value in which we want to train it against, right? So in this case, we just have a simple y equals 2x linear relationship for our data set. And we're kind of generating that on the fly using PyTorch. So that was kind of the gist of things with PyTorch, and we'll kind of get into the nitty gritty and little things associated with PyTorch and kind of the beginner stuff. But before that, does anyone have any questions with anything related to what is PyTorch, the data set stuff, the tensor tracking, anything? Okay, so we'll move into our live demo, which I assume should take up most of our time. I mean, this was only like 10 minutes. Basically, if you guys would like, you can open up a Google Colab. Any Colab is totally fine. Just go to google.com. You can create a new file in a collaboratory, and you could get something like this. And then basically you can set like, okay, your name for your file. And it's a blank Colab right here. And then you can select your runtime. In this case, if you guys have access, which I think everyone should have. I'm just going to use a different account because I have Pro on this account. If you're a student, you should be able to get Colab Premium, and you basically get all of these enhanced GPUs. but either way, I think everyone should have access to the T4 GPU. So if everyone wants to load that up, and then we can shortly begin kind of the interesting part of this lecture. But yeah, feel free to ask any questions, talk with anyone.
Can you show us what website to go to again?
Yeah. My bad. So if you go to, why did it?
Oh, is it collab.research.google?
Yeah, even if you just type Google Colab, you go here. It's the
Okay.
first link, right? And you can create new notebook right here.
Oh,
Yeah. So like I'll do the whole process again right here. Create a new notebook, and then it should load everything up, and then you're basically where I was initially, right here. So yeah. So yeah, you want to change your runtime type to this GPU preferably. You don't want to have it on the CPU, so we can kind of play with some of the things with Colab. But yeah. And the next lecture, I haven't really finalized what we're going to do for the next lecture. That's also the one, I'll be leading that one as well, and it's going to be the second in the series. But depending on how what happens today, I plan on kind of going into something specific or like industry related, whether it's NLP or with some images, some sort of transformers, hopefully. We'll see. Is everyone ready? Thumbs up? Are we all good? Okay, perfect. So the first thing that we want to do, right, is we want to import any sort of libraries that we need, right? So in this case, we're going to be using Torch, right? NumPy for simple data processing, right? And then I'll kind of play with the data stuff, so. And then we have our data loader, which I'll get into then. But you can basically, okay, so you can, if you haven't used Colab that much before, whatever code you type, you run it selectively. You can run it using Shift-Enter as the keyboard shortcut. So here I made an error. It's supposed to be from Torch, from the package you import these specific components, right? So the main thing that I wanted to show with tensors, the main like benefit, right, the vectorized operations, is that, okay, so you have this array right here, 1.0, 2.0, 3.0. This is a simple Python array, right? Now, if we were to print something like x plus x, we would get basically a concatenation of the array, right? That's not, yeah, sorry.
how does like it know what libraries to get? Because you haven't set up like a virtual environment.
I'm pretty sure it pulls based off of like the back end. Like it's a cloud run environment, so it just allocates whatever resources are necessary.
Okay, so whenever we just like import the libraries, it just like gives us whatever. It just gives us the libraries from their predetermined environment.
Yeah.
Okay.
Yeah. Yeah, that's the main like drawback. Sometimes you can run into issues with that. If you have your own virtual environment, you can set like specific versions of the libraries that you want to import. You can kind of nitpick everything. In this case, it's kind of up to like the backend or Google Colab for what to import. So you can run into issues with that. But again, the benefit of that is you don't have to worry about like NumPy 2.37 instead of like 2.4 not compatible with some random library that you were using, for example. Yeah, so in this case, we have this Python array, right, x plus x, and it prints 1.2.0. It just prints it twice, right? That's not what we would call a vectorized operation, in the sense that if we had a vector that was 1.0, 2.0, 3.0, if we were to add it with itself, the result would be something like 2.0, 4.0, and 6.0, right? So simple Pythonic array can't really do that. Now, if we were to declare this, right, as np.array, right, x, and we were to print this again, and then this time, right, we can now get 2, 4, and 6, right? So we get our vectorized operations with NumPy. But the thing is, when you declare some sort of, you can't have that hardware acceleration with NumPy, right? So if we define our device, let's say, this is how you usually kind of put things onto your GPU, right? This would be the line where you define your device CUDA, which is your GPU, if the CUDA is available. Otherwise, you call it a CPU. And so if you guys want to see what that looks like, in this case, if you guys selected the correct runtime, it would be device type equals CUDA, right? The benefit with Torch, right, is that you can do vectorized operations, but you can also put it on your GPU. So if we were to have x equals torch.tensorx, let's just rename these for clarity purposes, right? We want to be consistent with our variables right here. Right, so in this case, we can see that vectorized operation works. And then now if we see the torch version of x, the tensor version of x, right? You get the same thing as the NumPy array, but if you wanted to put it on your GPU, you can't really do that with your NumPy array. You can't really do 2.2 device, which is basically you're trying to move it to your GPU. You can't do that with NumPy, right? And that's the main point with Torch, is that if we were to kind of accelerate it in that sense, have these fast computations, we can do torch.x.2 device, right? And basically now you can see this specific tensor is on our GPU, right? And now we can do gradient tracking, optimizations, the computations are gonna be much faster, and you can slowly start to see why we would prefer a tensor instead of just a simple NumPy array. So that's that. I'm going to leave this here for now. Another thing I'd like to mention is with the GPU acceleration and everything is how we can do gradient tracking, right? So let's say we have something called x gradient equals torch.tensor, right? We create a tensor for 2.0 and then we enable gradient tracking, right? So we basically just created a tensor 2.0 and now it has gradient tracking. Let's display the initial gradient of this. And that would be something like, right, 2.0. So we basically don't really have a gradient for this yet, but if we were to have something along the lines of y equals x grade to the power of 2, right, and we were to do something with y dot backward at the specific value of 2, you can kind of see that how we can track a specific derivative at that point with respect to x, right? And if we had multiple variables, then we'll take the partial derivative with respect to every variable. Right? So in this case, we have our point 2.0, right? And you see that, okay, at y equals x gradient at that function that we have right here, x to the power of 2, right? You see that y is equal to 4, right? And gradient of y with respect to x gradient is 4.0. That makes sense because obviously the derivative of y with respect to x is 2x, right? And at the value of 2, that derivative is going to be equal to 4. Yes?
What does y dot backward do?
That computes the gradient, tracks the gradient. So it does a backward step and it computes the gradient. Yeah, so that'll be our gradient computation. In machine learning, when we have our model, the backward step with our neural network is back propagating, right, and computing the derivative of the loss function with respect to each of the weights, right? And then we up those weights respective to that. Okay, and then let's kind of move into more of a neural network architecture. I'm just double checking everything. Okay, so we're going to define basically the neural network class that I was talking about. We can do this by importing the specific import torch.nn as nn. That's going to be our class. And we can call it my nn, right? or we can just call it NN for short, neural network, right? Basically import it as NN.module, FNN. Okay, so we can kind of, basically the whole point of kind of doing this class is then we can kind of detail our own stack, or yes?
So what does it mean, like we are like passing in nn.module and we're calling like super.init, so like
Well, that's the superclass, so we're basically kind of initializing that, and this is like a subclass of that, so we can define our own like neural network as like an extension of that.
So we're defining a subclass of the parent class nn.module.
Yes.
And what is like nn.module?
Well, that's basically the main package that we're using
Okay.
to, yeah.
Okay, so like we can define our own neural network
Mhm.
by creating a child class of the parent class.
Yeah,
of
yeah,
module.
that's the main abstraction of PyTorch. Yeah. Thank you for the clarification.
It's also possible to go a little bit slower so I can type a little bit.
Yeah, sorry. Okay, so we have our linear layer. Basically, you can call this anything you want. You can call this layers, basically anything, because that's an internal variable. And then what you want to do, right? Now you can kind of define your own like sequential architecture, right? That passes through, right? So the first thing we might have is a linear layer that, let's say, takes in one input, right? And then has 64 hidden neurons. So that'll look something like, okay, we have one neuron, and then it connects to 64, another layer of 64, right? That's gonna be a linear layer, fully connected layer. And then we could add an activation function. Does anyone have any ideas for any activation functions, or anyone wanna suggest anything? Anything, like any benefits, maybe as to why we might prefer this one over the other one? That's a good one, but in this case, since this is going to be part of like the internal layers, I'm specifically looking for another activation function that we use. Sigmoid is usually used towards the end. Yeah. Yeah, that's the one I was looking for. There's also variations of that, particularly leaky ReLU that has normalization with that. Kind of, let's look at, okay, 553, that's fine. So if we look at ReLU right here, right, you see the activation function for specific points, right? It's more absolute in the sense that, okay, if we were to have sigmoid, right, we don't really want to have an issue with dying gradients, or the problem known as vanishing gradients, where throughout our neural network the gradients start to vanish and then there's nothing that's being updated, because obviously our updates depend on the gradients. Now if we have ReLU, then that helps us kind of have strong gradients flow through the network at all times, right? And that helps us kind of build and update the weights, right? And so sigmoid is something we want to have towards the end. And so, I mean, for now we can stick with ReLU. And then we can have another layer. Let's say we have one that's another 64 by 64. It connects to 64. Actually, let's make this like 48. Right, so this one, now the 64 layer connects to another layer of 48 neurons. And then we add another ReLU layer. I'm just gonna use tab complete here. And then we finally connect to our one output layer, which is one output feature, right? And so if we want to have what we would say as kind of like a forward pass function, right, to call on, as in the subclass, we would have this, right? And return self dot whatever our stack was called, and we just called it layers. So we could name this something like a linear stack to be a bit more descriptive for the next person. And then we can kind of do our input variable in the sense. So this should all, this should be capital. Right, so this should all compile. It should all work. And then we can basically initiate this as and then I mean, if we want to, we can also add some sort of parameterization with this. Like if we want to like make the 64 kind of up to the user, we could say like kind of like layer 1, call this layer 1, right? And change this to here. And we could kind of have right here, we can play a lot with this, right? Because again, this is all, at the end of the day, this is all object oriented, right? We can give it a default argument of 64 so we don't have to worry about it. And this would basically needs an argument. Oh shoot, I think, what am I doing wrong, bro? Do we need to pass this in as well? Gosh, sure, that's not right. Super object. Okay. I'm just supposed to call this as it's being used as a keyword instead of a function. Stupid mistake. Okay, sorry about that. So you can again declare this as basically with the default argument, and if you want to specify your layer 1, you can say, oh, okay, I don't want 64. I actually want let's say 72. Right? You can have kind of like in the level of abstraction with that, because again, all of this is Pythonic at the end of the day. And then you can also, I think this should have display functions, kind of like description functions, something, right? I think you could maybe magic typing, yeah, right here. So you can kind of just see here, you see your linear stack again. Your first layer is linear feature with in features 1, out feature 72. There's a bias on it. Does anyone remember what a bias is? So it says it has a bias on each of the neurons. What does that mean? We have a weight on the neuron, and then we also have a bias. No one remembers a bias? Damn. Oh shit. Should help too. So I'm gonna show a visualization. Kind of, okay, never mind. I'm gonna show with the linear regression. Right? So we have a simple linear regression equation right here, right? In this case, we have, okay, w times x, and we have a little bit of bias that shifts our output, right? So basically it's the same concept applied to each individual neuron, right? And there's also a thing called bias. We have bias and variance in the overall fitting of the neural network. Does anyone remember variance and bias in machine learning? Those two terms? What does it mean that we have high bias or high variance? Well, high bias basically means that we have inherent assumptions about our data. It's like training a linear regressor for, I don't know, like image classification. You know, it's like the linear relationship, you can't assume that to a bunch of images, so there's going to be an inherent bias and you're gonna make assumptions because the model is too simplistic. If we have high variance, that's like training a neural network to basically do y equals 2x plus 3. You could easily model that using a linear regression function, so you don't need to train a neural network with 48 layers. So there's absolutely no need for that. Okay, so we see that every layer has bias enabled. We see our activation functions, and then we can kind of go into our data set for this. This is kind of going to be very similar to our neural network class. We basically start off with, okay, let's call this one class data set. Same thing as Alvin described. We're basically going to declare a subclass of the parent class utility, and that way we can have a level of abstraction with, okay, we're using what's already provided to us, and then we can add levels of customization based off that. So data set is going to be our parent class, and then we have our initialization function that we do self. We pass in this case, I think the tutorial that I wrote, we're gonna kind of make it up along the way. The data in like kind of generates the y values as we import it into the accessor function. And then so we have self.data equals, and we gotta make it a tensor first. Torch, not tensor. And then we have this d-type parameter, which is basically our data type. We can call this float32. We can basically, I mean, there's multiple different options. You can do float16, you can do float8. I'm feeling a little special today, so I'm gonna do float16. And then we can have our length function, which is basically gonna give us the length of our data set, right? So the only parameter we need is self, and then we return the length of self.data, which autocomplete spoiled for me, so it's not very nice. And then we have the item function where we can get the individual items, which is going to be important, right, when we do our actual learning in batches. So we have self, and then we have this parameter, the index. So our data set, at what index do we want to return the data? So we're just going to call this idx, right? And so for this, we get self.data idx. We get our x values, right? That's going to be our input feature in our data set. So we're going to have a column for x. And then obviously, since we have a data set, we need to have some sort of truth value. So that's, let's say, let's just define this as a function. We can do x squared. Let's make it even more simple. X times 2 plus 10, right? And then we return x and y as tensors. Both of these are tensors, which is exactly what we want. All this should compile, and then we can kind of have example usage. And the way we want to do that is kind of like how we did it here, where we can use these same values, but let's just generate data. So let's make a loop where we go from 0 to 200, right? And and so basically, right, we created our data set by looping from 0 to 200. That's going to be our x values, right? And then we appended it to the data array. And then we can basically remember, because our initialization function, you only need the x values, right? We generate the y values when we get the item, right? So that's really neat in this specific case. And then you can see kind of what ds of 0 looks like. And it's basically, if you look at it, it's going to be an x pair and a y pair, and it matches with our linear equation, y equals 2x plus 10. If we look at, let's say, the end of it, which should be 199, and then multiply that plus times 2 plus 10, you get 408. So we basically have 200 data points off this linear equation. And we've created our own data set using PyTorch. We've created our own neural network. Obviously, we're not going to be using PyTorch to solve linear equations. That'd be really, really trivial. We'd be using this for something like image data, text data, any sort of complex data that requires something with a little more fitting to the data, and you can't really do it with classical ML. So we'll kind of get into that next week. And then now comes the fun part, which is training the neural network, right? In which we can kind of just, first thing we want to do is define our loss function. So before I do that, does anyone have any ideas for this linear equation that we have, a good loss function? Anyone? I mean, I said it earlier, what we'd use for linear regression, a loss function.
Mean squared error.
Yeah, so we want to use mean squared error, and that's already built into PyTorch. So if you look at that right there, you get n and that mean squared error loss. And then we can define our optimizer, which is how we're going to be updating everything. Most popular one is Atom. You can play with a couple others if you're really feeling quirky, but I mean, everyone usually sticks to Atom. And then you can set the learning rate, which you can set to a variety of different things. In this case, this is how we're going to update the weights, the speed at which we're going to update the weights. So for right now, let's stick with something like 0.001, or you can just use scientific notation. And then we also want to move our model, because that's where our weights are, right, to the GPU. So we do model.to, device, right? And now we can kind of do, okay, let's start some training. And I need to summon Colab right there. And then basically what we're going to do, we can define a couple of set variables before we do that. One thing that we need to do before we do this, I forgot to mention, is set up our data loader, which is basically how we're going to be, it's kind of like an intermediary between the data set that we have and the neural network. Is kind of our data loader, which is kind of pulling in the data set at specific batches, right? Providing it to the neural network we optimize, right? So that's kind of like, it's like if you had like kind of sort of like a factory, right? And you need to pull, let's say, supplies to build, I don't know, like a piece of candy. You would need some sort of mechanical arm or whatever. That would be your data loader to get the specific supplies and put it into place so we can build whatever we're doing. In this case, we can just simply call our thing data loader, and then we use the data loader class. So we define data set, batch size as 10, and then shuffle as true, which means that every run we're going to shuffle our data so the model doesn't overfit on it. And what I usually like to do, what's usually good practice, define some of these constants preemptively. So we want to define our batch size as 10. Usually for larger tasks, we do powers of 2, so like 16, 32, 64, 128. Our data set is around 200 data points, so let's stick to 16 for now. Let's train this for like 100 epochs. And then what else? We can just replace this here, and if we ever need to come back and change our batch size, we can go right here. So that's our data loader, and then we can start our actual training by doing for epoch and epochs. Oh shit, I didn't mean to run it. What we can do then is set the model into training mode, and then we can basically, the way we refer to our data loader is kind of within the for loop itself, right? So we can kind of do a simple Pythonic enumeration where we have inputs, we pull it in from the enumerate, we get our batch index, so it nicely separates everything as to inputs and labels. Our inputs again are X and Y. So for readability, let's fix that. you'll want someone else coming along, you know. And so we get those, we put them on our GPU, again, one of the main benefits of using PyTorch. And then what we can do is kind of do a forward pass, right? Compute our loss using our loss function that we defined here, right? Zero the gradients. Loss.backward would basically compute the gradients with respect to each of the individual weights. And then what's missing is optimizer.step, which in turn updates everything, right? And then so at the end of that, that would be that. And we've kind of already completed this batch of training. And then what we would usually like to do is kind of show the output of this specific training. Let's do it every 5 iterations. So modulus 5 in iterations of 5. So we print this. Training loss. All right. Okay. And then we have, let's say we want to do this to 4 decimal places. Alright, so if you take a kind of like a look at this, which is our training loop. Oh, we never ran this, I'm assuming, yep. Make sure to run all the cells in between, and then, oh yeah, made an error right there. Right here, so remember when we did float 16, that I'm pretty sure conflicts with our data type later on. So you want to change that back to float 32 right here. Oh shit. This is throwing this in there. Okay, we're getting an error in our model architecture. It shouldn't be happening. Let's just make this one for now. I believe our shape of the x variable is wrong. Might have to one times 16, 1 times 1. Alright, let's leverage some AI. Just okay, so the shape was wrong. This usually doesn't happen, but because this thing is super simple, the batch size was it was compressing it to a shape of just 16, it's a row vector, but for the input we need a column vector. So these two lines fixed it. But now you can kind of see once we do our training for this network that we've built, you see the training loss go down. Right, you see it slowly go down to 659, which honestly still I'd say pretty high. So let's raise the epochs to 500, which is kind of crazy. Let's change this to 5, so be a little bit more aggressive. And see, we kind of end with already something that's 10 times better, 100 times better to be more precise. Yeah, so now our loss is basically 0. Basically, we can capture the linear relationship quite well using this neural network, and it's now time for visualization. So let's say we have some inputs, right, outside of our distribution. Let's say -5, right? We only did positive values. And then let's say we had 300 and 400. Right? And then we do x dot 2 device. And then we put model in evaluation mode. And then we also have to do this, the way we evaluate our data set is we turn gradient tracking off. So we remove that, and then our predicted y values would be, we wrap this all in a tensor, and then that would be our predicted y. Okay. I'm gonna wrap this around in a tensor first. Right. There we go. So we get our predictions. Now to see how close they are, we can just take the item of that. We don't need this necessarily the torch. So we move it to the CPU, and then we take the item. Right, so we get 1.9 to the -6, which should be basically 0, right? So that's basically what our relationship captures, 2x plus 10. So -5 times 2 is -10, plus 10 is 0. And so the neural network predicts something that's that's basically close to 0. And then for other predictions, 300 and 400, we get 610, and we get 810. So again, we've been able to capture the linear relationship pretty well through 500 epochs of training on this neural network. To kind of reiterate what was happening before, I can kind of just do a quick overview before we end things today. So first, we kind of looked at why we'd want to use a tensor. We saw that, okay, we have vectorized operations, and that instead of, okay, if we wanted to add arrays, multiply arrays, and even move them to a device for quicker and better computation, that's why we want to use a tensor. And then if we want to build basically a neural network, we can create our own linear stack right here, and then train this with our custom data set that we can generate like this. And then we have our optimization function again with gradient tracking. We're leveraging that to do back propagation and therefore update the weights. And with training, it works pretty well. Probably realistically only need 100 epochs, but yeah, I think that should be it for today. Next week, again, I'll kind of look at some more advanced topics, but nothing too crazy, obviously, just kind of building off of this stuff related to NLP, LLMs, and other cool stuff that you can do with PyTorch. But yeah, thank you guys. That should be it.